Welcome to P. Clark Practical Calculus for the Busy Math Student. And here we're going to take a look at an example of finding horizontal and vertical tangents on a plane curve that's defined by a set of parametric equations. Here we're analyzing the plane curve for parametric equations defined as x equals the cosine of theta and y equals 2 times the sine of 2 theta. Theta here is going from 0 to 2 pi. And we see this kind of figure 8-shaped graph here, and we're trying to determine points of horizontal and vertical tangency on the graph. And so if we think about what that means to find horizontal and vertical tangents on the graph, we can see them, we can visualize where they are here, but how do we find their exact location? And it comes down to the definition of the derivative, the tangent line slope defined parametrically, which states that dy dx, rate of change of y with respect to x, is the ratio of dy dt divided by dx dt. And even the algebra of the differentials there proves that. So that's pretty self-evident, that first derivative definition for the parametrics. So if we want to find a horizontal tangent, that's defined as a tangent of 0. And so if we look at the definition here, it should make sense then. That's any place where dy dt is 0 and dx dt is not. Our other two kind of critical points here on a plane curve would be the vertical tangent. That's a tangent that's undefined, and so there we're looking for places where dy dt is not 0, but dx dt is. And then there's the third case, which does not seem to be apparent here, but we can prove if it's not there also, and that's called a non-smooth point. And a non-smooth point is a place where both the rate of change of y with respect to t and the rate of change of x with respect to t are 0. And it usually has some type of a cusp point if you're looking at a parametric curve and that occurs. So basically here, what we need to do is to find the derivatives of x and y with respect to the parameter, which in this case is theta, not t. You know, the definitions are written in t, but that really doesn't matter. And then find out when are those first derivatives with respect to the parameter 0. So we make a list of each of those, and then we compare them and see, well, which ones result in horizontal tangents, which ones vertical, and possibly are there any non-smooth points. So first thing we need to do here is to run our derivatives with respect to theta. So dx d theta is negative sine of theta and then dy d theta, little chain rule here, but it turns out to be 2 cosine 2 theta times 2, so 4 times the cosine of 2 theta. And again, it's worth remembering that here theta is between 0 and 2 pi. And that's typically the case when you have these trigonometric parametric equations where we tend to use theta as the parameter in that case. So anyway, we take the two first derivatives with respect to the parameter and we set them both equal to 0. So in the case of dx d theta, my equation is fairly simple. Negative sine of theta is 0. We have to go back into our trig class a little bit here. And now these are quadrant angles, so the best thing to do is probably just think of the sine curve, and the place where sine of theta is 0 would be 0, pi, and 2 pi. If we do the same thing for dy d theta, for cosine 2 theta is equal to 0. You might be a little careful with this one because this is a multiple angle trig equation. And you have to remember that when you have a multiple on the angle, you're also changing the period of the trig function. So when you state the solution the first time, you want to state the general solution here. So if the cosine of 2 theta is 0, that means that 2 theta is going to be either pi over 2 or 3 pi over 2 in the first positive rotation. But since it's a multiple angle case, I need to state the the general form. So for the first one, 2 theta is pi over 2 plus multiples of 2 pi. But then when I divide by 2 there, I have pi over 4 plus multiples of 1 pi. In a similar way, my second solution says that 2 theta is 3 pi over 2 plus multiples of 2 pi, which means my second solution, general form, is 3 pi over 4 plus multiples of pi. So if we write those out, we're just going to work our way around from 0 to 2 pi and make our list here of when dy d theta is 0. And so that's going to be pi over 4, 3 pi over 4, pi over 4 plus 1 pi, 5 pi over 4, and 3 pi over 4 plus 1 pi, so 7 pi over 4. Our next solution will be outside of the domain of theta, so that's it. So we have 3 places where dx d theta is 0, and we have 2 places where dy d theta is equal to 0. And if we notice, the first thing you probably want to do is to look at your list and see if there are any numbers that are on both of them, because if there are, then that's the definition of a non-smooth point, which in this case did not occur. So we have no places on this graph that are not differentiable, no non-smooth points. So then these define the horizontal and vertical tangents. We just have to keep them straight. So when dx d theta is 0 at 0 pi and 2 pi, dy d theta is not. And so those would be our vertical tangents. So that would be at theta equals 0, pi, and 2 pi. Now, the period of this graph is 2 pi, and so by the time we get around, it's going to actually be coming back to where it began here. So really we see 2 vertical tangents. I mean, obviously on the graph they're here and here, and if you want to figure out which one is which, at theta equals 0, my point is 1, 0, so that's over here, that's the one on the right, and then when theta is pi, then my point is going to be negative 1, 0, and that's this one over here. So that's the proof of it as far as the vertical tangents. And then that means that the places where dy d theta is 0 and dx d theta is not are my horizontal tangents. So again, those are pi over 4. And if we just work our way around here, when theta is pi over 4, then I have the cosine of that, square root of 2 over 2, and 2 times the sine of pi over 2. So that's square root of 2 over 2, 2. That's this point here. That's my first horizontal tangent. And we work our way around. So 3 pi over 4, I'm going to have negative square root of 2 over 2, 2, that point on the plane. At 5 pi over 4, my point is negative square root of 2 over 2 minus 2 on the plane. And then at 7 pi over 4, we have our fourth horizontal tangent at square root of 2 over 2, negative 2. So, nice example demonstrating how we can identify horizontal vertical tangents on a plane curve. And there's a possibility from time to time that you could have non-smooth as well. That did not occur here. And it's just a matter of taking the first derivatives with respect to the parameter, which in this case was theta, and analyzing when those are 0. If you'd like to learn more about parametric equations and their calculus, you can buy my textbooks available for a nice price on Amazon. Don't forget to subscribe to the P. Clark Calc channel. Until next time, I'm P. Clark.